Hello, welcome back to the channel. So let's do one last question on solving indefinite integrals using substitution. And again in this question we see the same quadratic expression over here. So let's use the completing the squares approach in order to simplify our quadratic expression over here and see if we can identify a pattern which will convince us to use trigonometric substitution in this case or not. So before watching this video, I would highly suggest you to first watch my previous videos where we have covered this concept in detail on converting quadratic equations into a meaningful form such that we can use trigonometric substitution to calculate the final answer to our complicated indefinite integrals over here. So in this question again, let's write this quadratic expression in the square root. So the quadratic expression is 3x squared plus 5x, and now let's use the completing the squares approach in order to simplify this expression over here. And in this case, for 3x squared plus 5x, if we add 5 by 2 root 3 whole square and subtract 5 by 2 root 3 whole square in this expression over here, we can convert this expression into a square expression over here, because we can write 3x square as simply root 3x whole square, 5x can be written as 5x, and then 5 by 2 root 3 whole square minus 5 by 2 root 3 whole square. And now you can clearly see over here, right? This is our A and this is our B. And now based on our A's and B's, if we calculate 2AB in this case, we will get 5 over here, right? So that is why this becomes root 3x plus 5 over 2 root 3 whole square minus 5 over 2 root 3 whole square, right? And now we simplified this quadratic expression over here into this form such that if we take our y to be, let's consider a new function y. If we consider our y to be root 3x plus 5 by 2 root 3, this expression over here will be changed to simply y square minus 5 over 2 root 3 whole square, right? And now this resembles our a square plus minus b square x square or a square plus minus b square y square term, which convinces us to use trigonometric substitution in order to solve for an integral which includes this expression over here, right? So now let's first write our original integral. Our original integral is calculating 1 by under root 3x square plus 5x dx. And then, since we converted this expression into a simpler form, which was root 3x plus 5 by 2 root 3 whole square minus 5 by 2 root 3 whole square over here. And now you also have a dx term over here. If you assume your y to be root 3x plus 5 by 2 root 3, your dy would be root 3 dx, right? So now this expression using this substitution can be easily converted to integral 1 over square root y square minus 5 by 2 root 3 whole square, and then your dx over here would be changed to simply dy by root 3, right? So this would be dy by root 3, and then your integral would just be 1 by square root 3 times 1 over y square minus 5 by 2 root 3 whole square dy in this case, right? And now we know a property about secant square and tan square theta, that secant square theta minus 1 is tan square theta. So if we assume in this case, we'll use the same approach that we used in the previous videos. So in this case, if we assume our y to be 5 by 2 root 3 secant theta, we can easily convert this expression as simply 5 by 2 root 3 whole square times secant square theta minus 1, right? Such that we'll get a square term in the square root, and taking the square root of a square term, we'll get the original term over here, right? So now let's clearly calculate what's happening in this case. And before doing that, let's calculate dy in this case as well. So dy would be 5 by 2 root 3 secant theta tan theta d theta, right? Because The derivative of secant theta is secant theta tan theta. And now after doing all the substitution, our final integral will become 1 by root 3 integral 1 upon square root 5 by 2 root 3 secant theta whole square minus 5 by 2 root 3 whole square, and our dy is 5 by 2 root 3 secant theta tan theta d theta. So 5 by 2 root 3 secant theta tan theta and d theta over here, right? So let's take this 5 by 2 root 3 out such that it will be multiplied with 1 by root 3, and this expression over here will be converted to 5 by 2 root 3 whole square times secant square theta minus 1, right? So let's do that. First, 1 by root 3 times 5 by 2 root 3 integral 1 over square root 5 by 2 root 3 whole square secant square theta minus 1 times secant theta tan theta d theta, right? So now this will be transformed to 1 by square root 3 5 by 2 square root 3 integral 1 over secant square theta minus 1 is tan square theta. So this would be 5 by 2 root 3 tan theta times secant theta tan theta d theta, right? And you can cancel this tan theta with this tan theta. You can also cancel this 5 by 2 root 3 with the 5 by 2 root 3 in the numerator, right? Such that your integral expression will be simplified to just calculating 1 by square root 3 times the integral of secant theta d theta, right? And since we were given in the question that you can use this identity over here, that the integral of secant x dx is log of secant x plus tan x. So if we use this property, this integral will be equal to 1 by square root 3 log of secant theta plus tan theta plus the constant of integration, right? We just use the given information in the question, right? The integral of secant x dx is log of secant x plus tan x plus the constant of integration, and that is what we used. So this answer that we got is in terms of theta. Now we'll have to do all those transformations back from theta to y and then from y to x in order to get the final answer, right? The same approach, the same process which we were doing in the last videos as well. So we know that our y is 5 by 2 root 3 secant theta, right? So you want the secant theta, which you already have. Secant theta in this case is basically 2 root 3 y by 5, right? And now you want a tan theta expression. So in order to calculate the tan theta expression, you know you'll construct a right angle triangle again. So let's construct a right angle triangle over here. If we assume this angle to be theta, we know that secant theta is basically hypotenuse upon base, right? Because it's the reciprocal of cos theta. So secant theta is hypotenuse upon base. Hypotenuse is 2 root 3 y. Base is 5. And now if you calculate this side over here using the Pythagoras theorem, you'll get this side as simply 2 root 3 y whole square minus 25 in this case, which can be simplified to 2 root 3 square is 4 times 3, so 12y square minus 25, right? So now if you want to calculate tan theta would be perpendicular upon base. Perpendicular, as we already calculated, is 12y square minus 25, the square root of that expression, upon base is 5, right? So you got your tan theta expression, you already had your secant theta expression. So now let's calculate the answer to this expression in terms of y over here. So we have this expression over here, and if we want the answer in terms of y, this would simply be 1 by square root 3 log of secant theta is 2 root 3 y by 5 plus tan theta is square root 12y square minus 25 by 5 plus the constant of integration over here, right? Now we'll convert our expression in terms of y to an expression in terms of x by using this expression over here, right? So we know that our y is this expression. If you want the final answer, the final answer to the original integral, you just have to substitute the value of y, which would be 1 by square root 3 times log of 2 square root 3 by 5 times root 3x plus 5 by 2 root 3 plus the square root of 12 times y square, which is this expression over here, minus 25 upon 5. So this is your log expression, and then at last you'll add the constant of integration over here, right? So this would be your final answer to the integral of this expression over here, right? So again, I know this was a complicated problem only because of the calculations involved in this question and not because of the approach that we used to calculate the answer to this indefinite integral over here, right? So that's it for this video. The main takeaway from this video is, again, whenever you have a quadratic expression, just use the completing the squares approach in order to simplify that expression into expressions like these. And then when you have expressions like these, think of if you can use trigonometric substitution in order to calculate the answer to your integrals over here, right? So feel free to comment down in this video if you have any doubts. Follow the channel in order to get notified about the other videos that I'll be uploading. Stay tuned. Thank you so much for watching. Bye bye. Take care.